In this episode, we're going to build a clear mental map of 4 web application vulnerability families that show up constantly in real incidents: injection, cross-site scripting, broken access control, and server-side request forgery. These topics can feel overwhelming at first because they sound like separate technical tricks, but a beginner-friendly way to understand them is to see them as different ways an application can be tricked into doing the wrong thing with trust. Web apps accept input, make decisions, and perform actions, and vulnerabilities happen when an attacker can supply input that changes what the app does in a way the designer did not intend. Sometimes that means the app runs attacker-controlled instructions. Sometimes it means the app hands privileges to the wrong person. And sometimes it means the app becomes a proxy that reaches internal resources on the attacker's behalf. We will keep this high level and concept first, because the goal is to help you recognize the patterns, understand why they matter, and connect them to practical risk without turning it into a coding tutorial. If you can spot these patterns, you can ask better security questions about any web app you encounter, even if you never write a single line of code. Injection is a broad category that is easier to understand if you think of it as confusing data with instructions. A web application is constantly passing input into interpreters like query engines, template processors, and command-like subsystems. When an app fails to separate what is supposed to be treated as data from what is treated as code, an attacker can craft input that the interpreter reads as instructions rather than content. The classic risk is that the attacker gains the ability to control queries, alter logic, or retrieve data they should not see. But the deeper issue is that injection attacks exploit the application's trust in its own internal language. Beginners sometimes assume injection is only about databases, but the same idea applies anywhere an interpreter exists, including searches, filters, and structured data formats. The fundamental security lesson is that anytime user input is placed into a context where special characters or syntax have meaning, the application must control how that input is parsed. When it does not, the attacker can reshape the program's behavior using nothing more than carefully chosen text. A practical way to recognize injection risk is to focus on the boundary where input becomes part of a structured statement. If you see an application that builds queries or rules by assembling strings, you should assume there is risk unless you know it uses safe binding techniques. You can also think in terms of intent. If the developer intended the input to be a value, like a name or an identifier, but the system treats it as part of a logic expression, then the attacker may be able to expand their control. Injection can lead to data theft, data alteration, and privilege escalation, but it can also be used to bypass security checks by changing the meaning of conditions. That means injection is not just about reading extra rows of data. It can be about changing the application's decision-making process. Beginners often fixate on the idea of stealing information, but the ability to change logic is sometimes even more damaging because it can undermine the entire trust model of the app. So when you think injection, think interpreter, think confusion between data and instructions, and think about both confidentiality and control. Cross-site scripting is a different pattern, but it also involves confusing data with code, just in a different place. In XSS, the attacker's goal is to get the victim's browser to run malicious script in the context of a trusted website. Browsers treat scripts as powerful because scripts can read and modify the page, interact with user actions, and sometimes access sensitive browser-stored data, depending on how the site is designed. If an application takes user-provided content and displays it to other users without proper handling, that content might be interpreted as script rather than plain text. When that happens, the attacker can effectively inject behavior into the site that runs as if it is part of the site itself. The danger is that the victim's browser trusts the site's origin, so it grants the injected script the same privileges it would grant legitimate site code. That can lead to session theft, account manipulation, and the ability to trick users into performing actions they did not intend. There are different flavors of XSS, but the conceptual core remains the same. Untrusted content becomes executable behavior in a trusted context. Sometimes the malicious content is stored by the application and served to many users later, and sometimes it is reflected immediately based on a request, and sometimes it is created by client-side logic that mishandles data in the browser. For beginners, you do not need to memorize these subtypes as separate topics. Instead, Focus on the question of where user-controlled content appears in a page and whether the browser could interpret it as code. A telling clue is when an app allows rich text, comments, or profile fields and then displays them dynamically. Another clue is when an app builds page content using raw input and inserts it into the page in a way that treats it as markup rather than text. The reason XSS matters so much is that it turns one user's input into a weapon against other users, and it uses the site's own trust relationship with the browser to amplify the attack. When you see XSS, you should also think about what sensitive data the browser has and what actions the user can perform while authenticated. Broken access control is a different family entirely, because it is not about code injection into an interpreter, but about permission logic that fails. Access control answers the question, who is allowed to do what? And in web apps, that usually involves checking identity and roles on every request that touches protected data or actions. A common beginner misconception is that if the user interface hides a button or the navigation doesn't show an admin page, the action is protected. But attackers do not need to use the user interface. They can make direct requests and change parameters. Broken access control happens when the server fails to enforce permissions consistently, allowing users to access data or actions that belong to others. This can look like reading another user's records by changing an identifier in a request, or performing an admin-only action because the server trusted a client-side role flag. It can also look like bypassing restrictions through predictable URLs or missing checks on certain endpoints. The core principle is that all access control must be enforced server-side, every time, based on reliable identity and authorization rules. To recognize access control risk, watch for patterns that assume trust in the client. If an app relies on the browser to tell it who the user is, what their role is, or what they are allowed to access, that is a red flag because clients can be manipulated. Another red flag is inconsistent enforcement, where some parts of the app check permissions and other parts do not, often because developers added features quickly and forgot to apply the same controls everywhere. Access control failures also show up when applications treat object identifiers as harmless, like assuming that if a user knows an order number, they must own that order. Attackers exploit that assumption by guessing or enumerating identifiers. The consequences can be severe because access control is the gateway to confidentiality and integrity in the app. If access control is broken, encryption in transit and secure login are not enough, because the server is still handing data to the wrong users or accepting actions from users who should not be able to perform them. Server-side request forgery is a vulnerability that often surprises beginners because it turns the server into the attacker's tool. In SSRF, an attacker influences the server to make an outbound request to a location chosen by the attacker. This might happen because an application fetches remote content, calls webhooks, loads images from a URL, or validates resources by requesting them. If the app accepts a URL or destination from the user and fails to restrict where it can connect, the attacker can cause the server to request internal resources that are not exposed to the internet. The key is that the request originates from the server's network position, not the attacker's, which can bypass network controls. For example, the server might be able to reach internal management services, metadata endpoints, or internal APIs that the attacker cannot reach directly. That makes SSRF a powerful pivot technique, especially in environments where internal services trust traffic from within the network. Recognizing SSRF risk often comes down to noticing features that let users influence server-side fetching. Anytime you see a feature that imports content from a user-provided location, previews links, fetches attachments, or integrates with external services, there is a potential pathway. The server may be following redirects, resolving names, or allowing unusual address formats, and attackers can use those behaviors to reach places the developer did not anticipate. The danger is not limited to reading internal data. SSRF can also be used to trigger actions in internal systems if those systems expose sensitive endpoints. Beginners often assume that internal equals safe, but internal systems sometimes have weaker authentication because they assume only trusted servers can reach them. SSRF breaks that assumption by letting an untrusted user indirectly speak through a trusted server. So when you hear SSRF, think of it as abusing the server's network privilege and identity rather than attacking the browser. These vulnerability families also connect to each other in ways that matter for risk. Injection can sometimes lead to access control bypass if it alters logic. XSS can lead to session theft, which then turns into access control abuse because the attacker is now acting as the victim. SSRF can expose internal secrets that enable deeper compromise, including credentials that allow privileged actions. Broken access control can make all other issues worse because it increases what an attacker can do once they find any foothold. This is why web app security often focuses on patterns rather than isolated flaws. The goal is to prevent a chain of small weaknesses from becoming a major breach. For a beginner, it's helpful to think in terms of attacker paths. How would an attacker go from controlling input to controlling actions, from controlling actions to accessing data, and from accessing data to expanding reach? When you see these vulnerabilities as steps in a chain, you understand why they are treated as top-tier risks. To wrap up, injection, XSS, broken access control, and SSRF are 4 ways web applications can be tricked into betraying their intended trust boundaries. Injection is about untrusted input being treated as instructions by an interpreter, allowing attackers to alter queries or logic. XSS is about untrusted content becoming executable script in a trusted browser context, enabling session abuse and user manipulation. Broken access control is about missing or inconsistent permission enforcement on the server, allowing users to access or change what they should not. SSRF is about letting untrusted users influence server-side requests, turning the server into a proxy that can reach internal resources. If you keep the trust boundary story in mind, you can recognize these vulnerabilities even without technical exploitation details. Most importantly, you can ask the right questions. Where does input go? Who enforces permissions? What executes in the browser? And what can the server reach on behalf of users? Those questions will help you spot risk early and understand why secure design choices matter.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.